This presentation describes an exciting, biblically inspired, gold-hydrogen prospect in southwest Oklahoma. My name is William Benzing. I live in Tulsa, Oklahoma, and I am an independent geophysicist/physics teacher with 30 years experience in oil and gas exploration with Conoco and national laboratories. The term gold hydrogen means hydrogen that is naturally formed in the earth and can be recovered using conventional oil and gas methods. Although I call the prospect a hydrogen gas prospect, it could be called a methane or helium prospect depending on the dominant gas in the reservoir. Because of geochemical considerations and worldwide exploration interest, I chose the gas reservoir to contain a considerable amount of hydrogen. About 4 years ago, in the Journal of Petroleum Technology, a new gold rush was announced. But in this case the gold was naturally occurring hydrogen in a former coal basin in France. Since then there is a worldwide push to find a reliable, sustainable and economically viable gold hydrogen discovery. I believe this prospect presentation can satisfy these requirements. As stated in the title of this presentation, the hydrogen prospect was biblically inspired by the scripture Job 28 verse 9, which states, "God puts his hand upon the rock, he overturns the mountains by the roots." This suggests that there are two sequential stages of rock deformation in the formation of buried mountain ranges. The first stage is the formation of mountains, most likely by lateral shearing in the crust, and then a second stage of deep crustal uplift which overturns the mountains. Without going into details, the next PowerPoint illustrates this two-stage process. Stage 1 mountain formation is shown on the left, displaying folded mountains with increasing fold frequency from bottom to top. On the right, Stage 1 folds have been structurally uplifted using an uplift grid and assuming that deformation is due to ductile shearing, which preserves the rock volume during uplift. Notice that as the fold frequency increases, the uplifted fold complexity increases with high-angle frontal folds and low-angle, back folds being created. The historical development of the gold hydrogen prospect is the result of integrating many years of geological, geochemical and geophysical revelations. I would like to point out specific revelations that were used to construct the prospect. The structural modeling method just shown utilizing uplift and ductile shearing, was conceived in 1990 while exploring the buried Wichita uplift for Conoco Oil Company. Comparing basement models with actual field data using geologic cross-sections across the Uinta uplift in Wyoming and the Wichita uplift in Oklahoma, the agreement is excellent, in support of the Job scripture. Another geologic revelation occurred in 1995 while I was applying my uplift with ductile shearing concept in southwest Oklahoma. As shown in this overhead, the traditional structural uplift model adopted by geologists assumed a very brittle rock response to deformation. As a result, the front side of the uplift appears as a stack of thrust faults with no significant structures on the back side of the uplift. This traditional model is merely conceptual in its construction. On the other hand, the novel model based on Job 28:9 and assuming a ductile shearing rock response can be mathematically modeled. Consequently, the structural modeling goes beyond merely conceptual thinking and visualization into predictive thinking and visualization. Notice that it predicts a possible low-lying, recumbent fold gas trap on the unexplored backside of the Wichita uplift. The next overhead confirms how a pre-uplift mountain fold can be overturned into a flat, structurally trapping, recumbent fold on the backside of a buried mountain.
This mechanical modeling method shows how to form a slightly recumbent, near-surface, transpressional fold into a flat, low-lying recumbent fold using crustal uplift combined with ductile shearing. The final fold strongly resembles a large-scale, low-lying recumbent fold in Greenland. The upper limb of the fold has been eroded by an unconformity. The height of the fold in the photograph is estimated to be about 2,500 feet.
A hypothetical gas-water contact, shown in red, has been added to the underside of the recumbent fold. Notice the underside of the modeled recumbent fold rises above the horizontal gas-water contact. This signifies vertical, structural closure, suggesting the possibility of trapping hydrogen below a low permeability granite seal. In 2004, I participated in drilling a 7,000-foot wildcat well in southwest Oklahoma. The well was drilled to confirm the presence of a flat-lying recumbent fold predicted by the structural modeling, which might trap gas under a thin, impermeable, granite cap rock. The granite cap rock was indicated by the presence of abandoned Permian gas wells, some of which penetrated granite at about 1,900 feet below the surface. There was no high-frequency seismic data available to help locate the position of the wildcat well. Unfortunately, the wildcat well didn't penetrate the granite cap rock. It was drilled to far down dip from the structural high and drilled through a thick section of iron-rich Arbuckle dolomite into sand and granite wash, suggesting a possible overturned geologic section. After setting casing, several porous zones in the dolomite were swabbed to test the formation fluid. When the formation brine was expelled into the drill pit, it was jet black and thought to be oil. However, the dark fluid sank to the bottom of the drill pit and eventually formed a black layer at the bottom of the pit. I had never seen or heard of this separation in all my years of oil and gas exploration. As will be shown next, the black formation fluid was due to the presence of mobile, nano-sized magnetite crystals in the dolomite porosity. As will be discussed later, the magnetite is a manifestation of hydrogen formation within the iron-rich dolomite, a key geochemical revelation. Assuming this is correct, the very low-density hydrogen gas, once formed, would migrate up dip into the structural high. Separation of the dispersed black nano-magnetite from the salt water was accomplished by flowing the mixture through a plexiglass tube which rested on large artificial magnets. Since the magnetite is ferromagnetic, it is attracted to the magnets and, as shown in the photo, accumulates inside the tube wall which rests on the magnets. After the magnetic material was separated from the salt water, it was analyzed to determine it was naturally occurring nanomagnetite. When compared to pure nanomagnetite created in a controlled laboratory, the carbonate rock created nanomagnetite was identical in terms of crystal shape and composition. These natural, magnetite nanoparticles are extremely reactive antioxidants. In the presence of 3% hydrogen peroxide and at room temperature, they readily decompose the solution into water and oxygen. These particles can play many different roles in redox chemical reactions. Now that the nanoparticles I recovered from a carbonate rock 20 years ago have been certified in terms of purity, size and redox activity, let's add 20 years of advanced, geochemical research and see how they could possibly play a role in hydrogen exploration. The question as to how magnetite nanoparticles could be formed in the pore space of a carbonate rock was answered in 2006 by a paper entitled Formation of Magnetite Nanoparticles by Thermal Decomposition of Iron-Bearing Carbonates, Implications for the Evidence of Fossil Life on Mars, by Alicia Cohn. In her abstract, she states that the thermal decomposition of iron-bearing carbonates to form magnetite nanoparticles was studied in order to better understand the parameters that control nanoparticle formation. Also, in a secondary electron image, where a cluster of magnetite particles appears white, she states that SEM observations revealed magnetite grains on the surface of the carbonate rather than embedded in the carbonate. This explains the presence of the nanomagnetite in the carbonate porosity. Most likely, there is no, preferred magnetic orientation to the particles, consequently, they are weakly held together and could be easily dispersed by fluid motion during swabbing, thus creating the black brine observed at the surface. Finally, the presence of iron in the drilled carbonate was verified using drill cuttings and a strong magnet. The cuttings were attracted when floated on a water raft. The significance of magnetite in the generation of white hydrogen is stated in a recent paper in Frontiers in Earth Science entitled Reassessing the Role of Magnetite During Natural Hydrogen Generation. This slide shows an SEM photograph of nano-magnetite with quotes from this significant research that I would like to read. Starting on the left it states, for the purpose of experiments, gold capsules filled with magnetite powder and H2O were run at 80 degrees centigrade and 200 degrees centigrade. After experimental alteration, high amounts of hydrogen were quantified. On the right, the paper states concerning hydrogen exploration, this work provides evidence that natural hydrogen can be generated at near ambient temperature. These statements lead to the bottom quote which reads, as for the future of native hydrogen exploration, these results demonstrate that magnetite-rich lithologies should be targeted while exploring natural hydrogen resources. In closing, the statement, magnetite-rich, certainly applies to the iron-rich carbonate rock that I drilled into 20 years ago. The formation swab was producing about 10 grams of nanomagnetite per gallon of brine. Among geochemists, the term serpentinization is a buzzword for hydrogen generation by means of a redox reaction between an iron-rich, carbonate dolomite and the mineral olivine in the presence of water with nanomagnetite serving as a catalyst. Recent experimental research points out that the nanomagnetite is actually a better hydrogen generator than olivine in the serpentinization process. I believe the presence of nanomagnetite in the porosity of dolomite rock can be considered a key indicator for hydrogen generation. The low-density hydrogen, once generated, should migrate up-dip and accumulate where a sealed, structural closure occurs. Based on the previous geologic and geochemical revelations, the gold-hydrogen prospect location is shown in this cross-section. The 5,500-foot prospect is located at the structurally high point of the flat-lying recumbent fold, Morotiles, in the center of several abandoned Permian gas fields. That makes sense assuming the shallow, abandoned gas fields are simply located above the high in the eroded recumbent fold. The Arbuckle dolomite serves two roles in the prospect. It is a source rock for the formation of hydrogen as well as a reservoir rock for the hydrogen gas field since the extremely buoyant hydrogen easily migrates up-dip into the reservoir. The primary gas in the reservoir is hydrogen based upon the presence of nanomagnetite in the down-dip wildcat well. Having discussed geologic and geochemical revelations, there is a very significant geophysical revelation that strongly supports the presence of a subgranite gas accumulation, namely a gravity anomaly. As shown in this overhead, the experimental uplift, structural modeling using ductile shearing, produces a uniquely shaped gas reservoir under a recumbent fold on the backside of a buried mountain. Structurally, a wing-shaped reservoir is formed. Just as a wing has a steep frontal side and a tapered back side, so does the structural closure which forms the gas reservoir. Based on this wing shape, a gravitational model, caused by the low-density gas reservoir was constructed. Because the slope of the wing is not horizontally symmetrical, the plot of the horizontal gradient has a non-symmetrical minimum at the point of maximum thickness. As shown in the gravity model, the horizontal gradient plot of the gravity response exhibits a steep slope to a minimum value at maximum reservoir thickness, then a gentler, tapered slope to the end of the reservoir. If the reservoir shape is correct, this should produce a unique horizontal gradient response on a gravity map. This overhead depicts the three-dimensional thickness of the low-density gas reservoir required to produce the gravity model in the dip and strike geologic directions. The three-dimensional model shape was revealed by 2.5D structural modeling of an uplifted and overturned pre-uplift mountain fold based on Job 28:9. The minimum in the horizontal gradient model occurs where the reservoir thickness is maximum, in this case region 4. In the dip direction, the color pattern is compressed on the leading edge and stretched out along the trailing edge of the wing-shaped reservoir. Let's now look at the buried Wichita uplift to see if the gravity anomaly is observed anywhere on the backside of the uplift. The uplifted, high-density, granitic basement rock of the buried Wichita uplift are easily visualized by using airborne gravimetry. The map on the left is the residual Bouguer gravity map, which shows areas of thick, dense igneous rock in pink signifying a buried mountain range running northwest to southeast in southwest Oklahoma. There is little color variation along the buried mountain range indicating a uniform, thick rock composition. On the right, a horizontal gradient map is calculated from the residual Bouguer gravity map on the left. The gradient data highlights small lateral changes in rock density. Notice the dramatic color change in the center of the uplift signifying a significant change in shallow rock density. Because the anomaly is located south of the steep mountain front, defined by the interpreted Mountain View Fault, the anomaly lies on the backside of the Wichita uplift. The triangular shape of the colorful anomaly looks very similar to the modeled gravity anomaly shown in the previous overhead. Let's take a closer look at the anomaly. This overhead shows a comparison between the field gravity data collected over the buried Wichita Mountains and the gravity model assuming a shallow, wing-shaped hydrogen reservoir that was created by uplift and ductile shearing. The similarity is striking, both in anomaly shape, orientation, and color distribution. Based on the field data, the prospective drilling location should be in the blue area where the reservoir thickness is maximum. Let me summarize the main points regarding the gold hydrogen prospect. Regarding prospect type, the prospect is a shallow, subgranite, structurally trapped, hydrogen reservoir within the buried Wichita Mountains of southwest Oklahoma. As shown in the structural cross-section, the prospect lies on the unexplored backside of the Wichita uplift underneath a low-lying recumbent fold and is sealed by a thin impervious granite caprock created by the Wichita unconformity. The reservoir rock is the iron-rich Arbuckle dolomite, which can be tested by drilling a 5,500-foot test hole. The test hole location is precisely identified by a distinctive, triangular-shaped gravitational data anomaly which is consistent with both geologic and gravitational modeling. Using the areal size of the anomaly, the prospect acreage is estimated to be between 10,000 to 28,000 acres. Based on these acreages, the estimated recoverable gas reserves, assuming the reservoir gas is 80% hydrogen, are 70 to 190 BCF of hydrogen. The next slide estimates the AAI value of the prospect assuming a hydrogen volume of 100 BCF. In addition, an AAI value is also shown for a pure methane reservoir gas. The estimated AAI value for 100 BCF of gold hydrogen, from a reservoir that contains 80% hydrogen and 20% methane, based on current March 2026 data, ranges from $680 million to $1.36 billion depending on the valuation method used, energy content versus mass. The estimated AAI value for 100 BCF of 100% methane gas, again based on March 2026 Henry Hub futures, ranges from $380 million to $400 million.